8.3, day number 1, separable differential equations. As a quick class opener, you can ask yourself this and pause the video. But what does it mean to solve an equation? And what is a solution? So to solve an equation, we find a solution. And this given solution satisfies the equation. I can't spell the equation. So very basic, if I said 5 equals 3x plus 2, I'd subtract 2, I divide by 3, and I see my solution to this equation is x equals 1. Let's talk a little bit about how we do that with a more complex situation with these differential equations. So again, just as a review, a differential equation includes a derivative. So dy dx is equal to, let's say, x squared is a differential equation. Why is it an equation? We got an equal sign. Why is it a differential equation? I have a derivative involved. Okay, so consider part B, the function whose slope is always the square of the x-coordinate. Okay, so the function is what we're trying to find. Right? The function is actually our solution. Now, our solution, I can't spell. Our solution is going to come first in what's called a general form. And then in the second part, we're going to identify a particular solution that would satisfy, would be satisfied by the point 1 4/3. Okay, so I've got this differential equation, and I knew going into it that I was going to use this, but let's look at the wording and determine how we would come up with that. So this function that we're talking about has a slope that is always the square of the x-coordinate. So the slope piece is talking about dy dx, and the square of the x-coordinate is what that says it is. Okay, so I want a function, or I want to find the function, or generally speaking, the family of functions whose derivative is x squared. Okay, so what we do is this process called separation of variables. You'll notice that I've got variables x and y. I want to split them up. Okay, some differential equations are not going to be separable. We'll talk about further techniques with that, but what we have talked about so far is this idea of slope fields to visualize solutions to those differential equations. Okay, so let's separate the variables. I'm going to multiply both sides by dx. And in doing so, I have separated my variables. Now you can think of this as 1 times dy. And now we have this in a form where, of course, it's an equation with our variables separated. All variables y on the left, all variables x on the right. And now what I'm going to do is I'm going to execute integration. Right? I'm going to find antiderivatives here. Okay, so if I antidifferentiate or find the antiderivative of 1 with respect to y, I would get y plus, I'm going to call this c1. Okay, of course we add that constant of integration. On the right side, I get x cubed over 3 plus, I'll call this c2. Now this will be the only time I use c on both sides of the equation. From now on, I'm just going to do the execution step I'm about to show you here, which is I'm going to subtract c1 from both sides, and c2 minus c1 is still just a constant. So I would leave it as y equals x cubed over 3 plus c. Now if you think about it, what is the derivative with respect to x of x cubed over 3 plus c? Well, that would be 3x squared over 3 plus 0, which is exactly what I wanted it to be, right? dy dx is equal to x squared. So here I have my general solution. This provides for us a family of functions with an infinite number of members whose derivative such that dy dx is equal to x squared. Okay, so let's visualize real quick the slope field. Now, take this slope field for dy dx equals x squared. Okay, so let's say dy dx equals 0. Well, where does x squared equal 0? Always at 0. Nowhere else. Okay, where would dy dx equal 1? Where is x squared equal to 1? Well, at positive and negative 1. These are not my best little slopes here, but you're kind of going to get the picture here. Okay, I'm using this idea of isoclines and nullclines. Here's a nullcline, here's an isocline. Let's go with 4. Well, that would be true when x is equal to plus or minus 2. Okay, so slopes are 4, and x equals plus or minus 2. Okay, so you might already be seeing the family of functions would satisfy the derivative y dy dx equals x squared. So check it out here. I'll just kind of pick an initial point and kind of do something like that. So let's say we just call that, one of our family of functions that satisfies this differential equation. Here's another one. There's y2. Right? And we could go on and on and on and on and on in both directions. All right, let's call this y sub k. All right, so that's our general solution to this differential equation. Okay, it has not identified a specific function until we employ this initial condition right here, 1/4. So our next step in going to find the particular solution is we employ this initial condition, 1/4. So I'm going to plug 1 in for x, 4/3 in for y. I'm going to solve for c, and that'll give me my particular solution. All right, so let's do the work to find the particular solution. So 4/3 is y, 1 is x. Let's solve for c to find the solution to the differential equation that passes through the point 1/4. Okay, so clearly I'm going to get 3/3 is equal to c. Therefore, our particular solution to this differential equation, which satisfies the point 1/4, will be y equals x cubed over 3 plus 1. All right, so let's find the point 1/4. Okay, how about like right there? Actually, let's go with, I guess it doesn't matter. But here would be our particular solution, right? This specific solution here that we found that satisfies that condition. Okay, let's continue with another example. Okay, so a differential equation is an equation which involves derivatives and whose solution is a function. Okay, so that's very key. The solution to these equations are functions. So for each of the following examples, find the general solution and the particular if you know what point it passes through. Okay, let's look at example 1. This will be a pretty interesting example. I can't get this to not be, there we go, that's a little better. All right, so first thing that I want to do is I want to separate my variables. All right, so I'm going to separate the x's and the y's. I'm going to multiply both sides by dx, both sides by dy. So I will get y dy is equal to x dx. All right, you can see that I've got a function in terms of y times dy, a function in terms of x times dx, and now I go to the next step, which is integration. I'm going to integrate both sides. On the left side, I get y squared over 2. On the right, I get x squared over 2 plus c. I've consolidated that constant of integration on the right side. Okay, I'm going to go a step further. Right, this is y squared equals x squared plus c. I just multiplied both sides by 2, and 2 times c is still just c. Now these are both very acceptable general solutions. Okay, you may choose to go a little further. I'm going to take this slightly further and write this as y equals plus or minus the square root of x squared plus c. So this last part here, right, this will be the form that our particular solution comes in. But I'm actually going to use this form to identify something very important. Okay, so let's get into that piece of it. I'm going to use this with our initial condition. So y squared is equal to x squared plus c. This is going to help me find the value for c. Okay, and I take my initial condition, which is 2, 4. I substitute in a 4 for y, which gives me 4 squared is equal to 2 squared plus c. Looks like c here will equal 12. Okay, so if I took this particular solution, which is plus or minus the square root of x squared plus 12, and I attempted to use my condition 2, 4, what you'll notice is that if I plug in a 2 and a 4, one of these plus or minus will not satisfy this particular point. Okay, so let's say I take 4 is equal to the positive square root of 4 plus 12, which is true, right? The square root of 16 is 4, so that checks. But if I go the other way and say that y, which is 4, is equal to the opposite of the square root of 4 plus 12, that's not true, right? So this is not considered part of that particular solution. Our particular solution for the example 1 that we've covered would only be the positive portion of the square root. Okay, so let's take a look now at the second part of this. Nice little caveat here. What about the point through to negative 4? Well, clearly to negative 4, we would go through the exact same process, and the particular solution there would be the other half of this general solution. Okay, now what I want you to see visually is this. The graph of y squared is equal to x squared plus 12, which is equivalent to y equal to plus or minus the square root of x squared plus 12. Actually looks like this, right? If x equals 0, y equals plus or minus the square root of 12. Okay, so that'd be 0 root 12, and this would be 0 negative root 12. Okay, and then the graph takes off in a parabolic sense in opposite directions. Okay, so the point 2, 4, which we highlighted above, ended up right here. And this portion of the graph, right, is our general solution from the first part of this problem. Okay, the point 2, negative 4, right about here, is satisfying this portion of the graph. Very interesting. All right, let's look at another example here. Okay, dy dx equals this ugly thing. Okay, well, I got to use properties of exponents here real quick to be able to separate this. So I'm going to use properties of exponents and rational exponents at that to write this as x squared times y to the 1/3 power. If I distribute that 1/3 to both of the terms, I get x to the 2/3 times y to the 1/3. Okay, so now we're in a situation where we can separate. Here we got multiplication. I like that. I'm going to divide both sides by y to the 1/3 and multiply both sides by dx. That gives me y to the negative 1/3 times dy is equal to x to the 2/3 times dx. Now, if you prefer to write the left side as 1 over y to the 1/3, by all means, go for it. I don't prefer that because it's just harder to see the power rule in place. So that could be what you like. Go for it. Okay, now let's integrate. We are separated. Let's integrate this thing. Okay, if I use the power rule here, I will have 3/2 y to the 2/3. If you question that, go ahead and take its derivative and make sure that it aligns with the integrand above. Okay, for x to the 2/3, I'll have 3/5 x to the 5/3 plus c. Okay, now again, this is an acceptable general solution, and all we're looking for here is a general solution, seeing that we are given no condition. I would likely write this as y to the 2/3 is equal to 2/5, right? If I multiply both sides by 2/3, I would get 2/5 x to the 5/3 plus c. And if you take it just a tad further, raising both sides of this equation to the 3/2 power, be careful please. If I raise this to the 3/2 power, I'm technically taking an even root of that both sides, so I'm going to tag on plus or minus 2/5 x to the 5/3 plus c to the 3/2. Okay, the reason for the plus or minus is this 2 right here, right, an even root. All right, let's look at one more example. Okay, example 3, we've got dy dx. We've got the square root of x divided by y. Looks like we're going to look for a general solution, then a particular solution. So let's separate this thing. I'll use some properties that I'm aware of. Right, rewrite this right side as the square root of x over the square root of y. Separate my variables. That'll be y to the 1/2 dy is equal to x to the 1/2 dx. All right, we're ready to integrate here. Okay, I'll get 2/3 y to the 3/2 is equal to 2/3 x to the 3/2 plus c. Okay, so is that a general solution? Yes, it is. Likely we'll want you to go a little bit further. I'm going to multiply both sides by 3/2. So I'll get y to the 3/2 is equal to x to the 3/2 plus c. And at this point, I'm going to call that a general solution. I'm going to employ my initial condition. Okay, if I employ that initial condition, what I end up getting is I'll plug a 9 in for y, plug a 0 in for x. Well, 0 to the power of 3/2 is 0. Therefore, 9 to the 3/2 is equal to c. So how do I write this? This would be 9 to the 1/2 to the 3rd. 9 to the 1/2 is 3. That's the square root of 9. 3 cubed is 27. So it looks like c is equal to 27. Now I'm going to write this as my particular solution as y to the 3/2 is equal to x to the 3/2 plus 27. And going just a tad further, I think I said 3/2 and wrote 3/3. There we go. Good work. I'm going to write this as y equals x to the 3/2 plus 27 to the 2/3. Now notice I don't need plus or minus here. Okay. 1, because 0, 9 will satisfy this. And 2, because I have a cube root here. So I don't have to worry about the duplicated outputs that would happen there. Okay, so there you have it. There's our particular solution to example 3. And our general solution, which could be written in multiple forms. I left it in this form right here. Okay, let's look at example 4 real quick. Now, example 4 is not separable. Many students will try to separate this and write this as dy minus y is equal to x dx. That's just not going to work with our formatting for integration. Okay, this is not a separable differential equation. There are advanced techniques that you'll learn in BC Calc and other classes potentially, which can kind of work through the issues of the separation on this. It's basically a separation through substitution, but that's not covered in this course. So for the purposes of this course, what we would do is we would say this is not separable. Okay, and we would visualize our solutions. That I just came up with that. That's pretty good. You can applaud there. Using slope fields. Okay, so you could use a slope field to kind of visualize the solution to that differential equation. All right, guys, that's 8.3, day number 1. See you in the next video.